it should be okay. Yeah. So, no one coming?
Yeah, others are coming.
Yeah, so essentially this is it. I mean, we don't have much more to say. It's just basic idea. We can split deliberately the topology of our systems, particularly PKM, and that's it. Yeah, okay. Maybe the final word is that what we're going to do is to derive a model for the kinematic tree structure, as you do for robotic arms in general, and the joint coordinate, because each of the joints has certain coordinates, that angle, safety, they are given. We will put them in a vector, and the vector is called theta. This comes later on anyway. I don't know. I mean, I had a few slides on the degree of freedom. I'm not sure if this is our main topic. Maybe briefly. So the good question, which is easy to answer, what's the degree of freedom of the system? Apparently it's all the same, right? One. So what does it mean to have 1 degree of freedom? It means that you need 1 input, right? Okay. The difference, of course, is the motion. I mean, the degree of freedom is one thing. They call it, so and there's this term mobility. Many times you hear interchangeably used DOF, degree of freedom, and mobility. But then you have to be careful, because mobility is different from degree of freedom. The degree of freedom is a number, right? So the degree of freedom is just an integer number. It tells you how many inputs you need, for example. The mobility is different. The mobility tells you how the system can move. Okay, how the system can move is not a number, it's something different. And how the system could move, because they all have the same degree of freedom, 1. But they move differently, right? And in particular, and even this one is different. So essentially what you see here is, it's the same linkage, they call it. It's the same, even the same geometry. But if you disassemble that one and assemble it in the other one, you end up here, right? So what you could do, for example, is to split it here or somewhere. I don't know. To cut, for example, take this off, take, I don't know, the purple one off. Move the whole system up there, put it again, and you're there. So it's the same system, I mean the same linkage, a different mobility, but the same degree of freedom. And here it's also different, and we have singularities and so on, but that's not important. What's important is to see the connection between the topology and the degree of freedom. This is just a bunch of pictures. This is all forward mechanisms. They all have different degrees of freedom, right? I don't know. This was the one, the spherical mechanism I've been showing before. You know, this is 1 degree of freedom, because you can move, and you know, this can go like this and then move on a sphere, because the joint axes are intersecting all the time. The same is here, but the motion is different. Yeah, you don't have time. As I was saying, it's not our main topic. But look at this one, for example. This again is a planar forward mechanism, and it can move. It can move in a plane, like this can go forward and upward, like, you know, you can do like this, okay? But if you have, for example, 1 link equal to the sum of the 3 links, then you're here. Same topology, but this is immobile, right? This is shaky but immobile. It's like a structure that is shaky, and there are a bit of dangerous situations there. Yeah, anyway, and then there's this Bennett mechanism, if you are mechanism theory, that again is having 1 degree of freedom, but not this kind of simple geometry with intersecting axes, but this is a very special kind of geometry that we as a center. Anyway, so what I would like to at least mention is a kind of a way of estimating the degree of freedom from a topology. Let's say that you are moving in a plane, right? Yeah. Let's say we are still having this planar motion. Again, this is this forward mechanism, you can move in a plane, right? How do you can estimate the degree of freedom? Look, start here, for example. So we have, let's say, 1 link is fixed, and let's say we're working on stationary systems. So I don't know, maybe this one. This one is fixed, okay? And then we have the 3 moving, the 3 mobile links, right? So S, maybe just to repeat, like here. This is essentially this one. Hello? Yeah. So it's essentially this one. So we have the fixed link, which is not shown here, and then you have the three moving links. Okay? And this is what I'm talking about here. So how do you start maybe estimating the degree of freedom? So let's say that all of the bodies would be unconstrained. Okay? So there are no joints. Okay? So this of course is not moving, this is the ground. We have three moving bodies. And let's say that we have let's say we have NB bodies. The number of bodies is NB. So we have four bodies here. Okay? So n equals four bodies, but only n minus one or more by, because the one is the ground. Okay, so and how many? So n minus one. And how many degrees of freedom does a body have in a plane? 3, right? So it can move in a plane with 3 degrees of freedom. So it can translate and rotate upon the vertical axis, right? So that means each of the moving bodies, the n minus 1 bodies, has 3 degrees of freedom. So the whole system, without being connected by joints, has 3 times n minus 1 degrees of freedom. Okay, but now we have the joints in it. So we have like we have nj joints, right? So, okay, how many so a joint has a joint degree of freedom, right? So it's the number of independent motions it can generate or allows to. And so the Revelet joint, for example, has 1 degree of freedom. Okay? And how many constraints does it impose? So now a joint with n degrees or nj degrees of freedom, like the Revelet joint, how many constraints does it impose? So let's say you have two bodies connected by a Revelet joint. How many constraints are imposed by the joint, by the Revelet joint? But the other question is, what can the bodies not do anymore because of the joint? Well, first of all, I mean, if you have a Revelet joint, what does it do? It restricts the relative motion of the two bodies to pure rotation. But that's why it's called the Revelet joint, right? So there are no translations anymore, right? So all the 3 translations, and in the plane, the 2 translations of constraint. Okay, and that's actually it. I mean, for the Revelet joint in the plane, there are 2 constraints, because it just says they must all the time intersect at this point. Right? The rotation is free, the translation is fixed. So that means for a Revelet joint in a plane, we have 2 constraints of freedom, 2 constraints, 1 degree of freedom. Now, if you do the math, actually, you see it's always like this. So you have like 3 minus the number of degrees of freedom. Let's say that, I don't know what to say in the plane. The plane doesn't make sense. Now in space, for example, let's say this is a spatial space, right? Okay. My assumption was the following. My assumption was, that's why I have the number 3 here, that all the bodies can only move in a plane. Now, if I would say all the bodies could move in space, for example, then they would have 6 degrees of freedom, right? And how many constraints would the Revelet joint impose? Huh?
Restrict translation.
Yeah.
Translation in all 2 axes.
Yes.
2 axes.
So translation in all axes?
No, 2 axes.
No, the translation.
In 2 axes, because the third axis, suppose it's...
No, it's a pure Revelet joint. It's not what they call a cylindrical. It can only rotate. It cannot rotate and go like this.
Okay, then it's 3 axes.
Yes, correct. So, and eventually we have 5 constraints. Because you have the 3 translations plus the 2 orientation about this axis and that axis. Okay? And for any joint, this is the general kind of formula, is that we have 6 minus the number of degrees of freedom of the joint. Okay? Now in the plane it is not 6, it is 3. So it's off.
6 minus.
Yeah, so in our case, it's because you're on the plane, you only have 3 degrees of freedom, and the number is 3 minus the degrees of freedom of the joint. I didn't do anything. Maybe it's me.
Cell.
Empty, maybe. Yeah, I think it's empty. Maybe it's a bit too loud. No, maybe. Yeah. So let's stick in a plane for the time being. So we said that each of the joints has 3 minus the number of degrees of freedom of the joint degree of freedom as constraint. So that means actually from the whole big number, 3 times this term, of the bodies without actually any joints, we subtract exactly this number. For each joint, 3 minus f, if fj is the degree of freedom of the joint. Okay, and there we go. And of course you can, take this into the sum. What do I do here? So the only sum is here. This is nj times 3. This is this, and then we have the same here. So essentially nb times 3 minus nj times 3 is this plus 1 and this there. Okay, so why I'm having this formula is simply because this is known as the Euler number of the graph or the cyclomatic number of the graph. So essentially what this is actually, yeah, it's here. I should have said it maybe separately. This number is the number of independent fundamental cycles of the graph, and that's unique. So whenever you have a graph, I mean this is essentially the message, right? When you have a graph, a topological graph, the only thing you have to count is the number of bodies, and then, the number of vertices, and the number of edges, which is the number of joints. And then you have to say, is it a planar mechanism? Then it's exactly this one. Or you have a spatial mechanism, then the 3 becomes 6, as we said before. And that's it. So this is well known. This is normally called the Grübler-Chebyshev-Kutzbach formula. There are many names for this. But this is, maybe you have it in a different term in your lecture, so many different names for the same thing. It normally works, but it of course sometimes doesn't work. But anyway, it's an estimate, right? And it's an estimate that you learn in mechanics courses, and it makes perfect sense. Even though it's not always possible, for example, for our mechanism here, that was our PKM. If you do the counting, so what we said is, of course, this is a spatial mechanism because we are moving in space, right? What you have is like 12, 12 bodies. 12 bodies, exactly, minus 6 times, so, what was this, 12? No, what's it? 12 into... yeah, the number is like this. The number of joints minus, where's the 6? 6 is, where's 6? Oh, 6. Okay.
6,
yeah, that was the example here. Yeah, for this, for example, it works, right? Yeah, but for the 6 is, so anyway, it's, what is it then? It's the number, yeah, so you have to sum up the joint degrees of freedom, minus 6 times, and now comes this. So the number of joints, number of bodies plus 1. Okay, the number of, no, sorry, I'm not using the number of bodies minus the number of joints plus 1. Okay, this is apparently 2, that's right. 2, yeah, right. So 12 minus 6 times 2 is 12, is 0, which is 1. Right? So anyway, it's an estimate. And it's so the Grübler-Kutzbach formula is what is it then? It's a lower estimate. It can be higher. Why it can be higher? Because it doesn't, this formula is only a topological formula. You don't care about the geometry. But there might be some special geometries which make some of the constraints redundant. And this happens here in this mechanism, for example. For example, what if you just consider, I don't know, it's too much to explain. Yeah, so this is the message. Okay, and I think we're running out again of battery. Okay, and there are other mechanisms just to show you some nice animations. This is called the Wunderlich mechanism. So just to say, there are mechanisms actually that can change their degree of freedom without disassembling it. Okay, so this is a 12-bar mechanism. It's a bit weird, but anyway, so it can do something, right? Maybe stop somewhere. Oops, stop. Oh, no, okay. So you have like 1, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 links, and then you have 12 joints. And that's it. Because of the special geometry, it can actually, when it's like folded like this, like now, it was now. It can actually split between two motion modes, right? Without actually disassembling it. Now maybe take the next one. Is it only 1 or 2 batteries? Is it only 1 or 2 batteries? Okay, this is just a side effect. If you're interested in this stuff, there's a whole community working on this so-called kinematotropic mechanisms and so on. Okay, we should stop and go to some more relevant, there we are, here, topic for us, because we need to really go into the modeling. Yeah, unfortunately, we need really to start with basics. It's a bit boring, but we have to do this. Sorry for this. It's about rigid body motions. I guess everybody knows what rigid body motion is, but in the end, there are so many different ways of representing them, modeling them, that we need to maybe start from a bit more deeper. Okay, it's all about frames. I know, maybe boring, but just I have to, introduce it. So we look at frames because a rigid body, kinematically, is just a frame, right? So once you have attached a frame to a rigid body, you know exactly how the body moves, and you know exactly how any point in the body is moving because of the rigidity assumption, right? Yeah. So what is a frame? A frame is essentially a point. Let's say start with maybe a triad. So we have 3 orthogonal vectors in Euclidean space, and they are located at a certain point. So 3 vectors, orthogonal vectors, in space, and they are located somewhere. Okay. So essentially, a frame is consisting of 4 elements, like the 3 vectors plus a point in space. And just to remember, a point is not a vector. A point is a point, right? So anyway. So yeah, as I was saying, once you have actually affixed a frame to rigid body, then you know everything about the rigid body motion. The only thing now, the only question is, how do you describe the frame motion? I mean, how do you describe the orientation and the displacement of the frame? Okay, yeah. And if you, for example, just to maybe show you this, so that was for one single frame, right? So the one frame attached to one single rigid body is nice, but if you look at these multi-body systems, I mean, these big systems, this is a bit of a part of a car chassis. And if you look carefully, unfortunately it's not so good to see, there's so many frames in here. It's all about frames. I mean, kinematics is all about frames. And there are so many frames. I mean, there's one here, there's one here. I don't know, every part has frames, at least one, many frames usually. And for this simple mechanism here, of course, each of the bodies, like here, there's a frame. There's always one somewhere in the middle, which is actually representing the body. And then there's always one frame on each of the bodies. I mean, okay, so the red one and the blue one, the bodies are connected by a revolute joint again, simple thing. And for each of for the revolute joint, at each of the bodies, you get one frame, right? Because in the end, the revolute joint describes the relative motion of 2 frames on the body. And you see, and this goes for all the revolute joints. So for the joints, you have 2 frames. For the body, you have at least 1 frame, and so on. So it's all about frames. So we need to understand how we keep dealing with the frames. And of course, these vectors, they have no meaning to us. I mean, no real meaning to us. But why I'm saying this, maybe a bit strange sentence, these are geometric vectors. Okay, and in the end, when you're computing something, you need numbers, right? That means that you have to somehow associate to these geometric vectors some coordinates. Okay, so let's say we have a frame, and let's call this Fi. And usually I is supposed to mean inertia frame. Do you know what an inertial frame is? The inertial frame is one that is fixed to the ground, so to say. So it's not moving. It's a non-moving inertial. A non-moving frame is an inertial frame. Okay, so good. Okay, and let's say we have given a vector, just any vector R, and the vector R is so. And I have when I have this arrow on top of it, this means like a geometric vector, something you cannot really pinpoint with numbers. It's just a concept of a vector. Okay, and what I can do, and I guess you know this stuff, I can of course project this vector onto the frame, axis. Okay, so I take the scalar product of the vector with, for example, the one axis. This is the one axis. Okay, and what I'm getting is then this. So the projection of this vector onto the one axis gives you that part. Onto the three axis gives you this part, and you know what I'm talking about, right? And why I'm doing this is because then I can actually represent this vector in the frame. And in the frame, it's like I take so much of the one axis, I take so much of the three axis, and I take so much of the two axis. And by saying this, I say the scalar product R1 times the unit vector E1, and so on and so on, gives you the vector represented in the frame. And essentially, we're only working with the coordinate, with the three components that we so computed, which is then put into a vector, and this is actually the coordinate vector, and this is the vector we are going to use. An important notation, and that's why I'm kind of stressing all this stuff here. So when you get the numbers, they have no meaning, unless someone tells you what they mean. That's clear, I guess. But in order to say what they mean, we use a leading superscript, right, to indicate the frame in which these components are expressed. So when you have a vector R, I can express a vector R in different frames, right? But I have to say in which frame they are expressed, and to say these are the components when I represent this vector in the frame I, then this is the vector. I mean, this three-component vector, or coordinate vector. Okay, so of course I can. Oh, yeah, what's this? Yeah. Oh yeah, that's what I've said actually. Yeah. Okay, I can of course do the same in a different. There's my vector. Anyway, so the vector is supposed to be here still. I don't know, somehow it's gone. I can represent it of course in a different frame, right? In, let's say, the green frame. And then I do the same. Of course, the only thing changes is the frame changes. That means this kind of superscript changes. And of course here, of course, everything changes. Now we have the green basis, and that's it. So, of course, we can do this, right? You can have any frame, any color. The thing is, how do you go from one to the other? That's the point, and of course this goes via so-called rotation matrices. Okay? So a rotation matrix is the one that transforms the coordinates in the, I don't know, in the I frame, for example, to those in the K frame. Okay? And that's what you normally call a rotation matrix. And the rotation matrix has entries. You know, it's a 3 times 3 matrix. That means like 9 components. And the components, they look like this. Essentially, these are the scalar products of the, you know, the basis vector of the frame from which you are rotating. I mean, from which you are transforming. The I frame times the respective one that is the row 1, 2, 3 of the target frame. And in the end, I mean, this is not so important, but in the end, you get the matrix. And that's the rotation matrix. So before proceeding, are you somehow familiar with this stuff? Rotation matrices? Huh? No?
Yes.
Hmm? Oh, okay. Good. Because otherwise we could talk a bit more about this. Okay. Okay, good. Let's say that we have a rotation matrix. What are properties of rotation matrices? I mean, essentially, this is what you see here. I mean, if you look at what is this meaning here? Who's good at math? So essentially, what you do represent the axis of the green frame in the. So this vector actually here is that one. And essentially what it is, it's the representation of the one axis in the I frame represented in the K frame, right? because you do the scalar product with the respective axis of the grid frame in the one frame. And essentially this is the meaning of the columns of the rotation matrices. And maybe this is not so important, but the message is we have unit vectors in here. And this is important. We have unit vectors and they are orthogonal. Because this leads you to some properties. When you take the, for example, the transpose times the, R transpose times R, like rotation matrix transpose times the rotation matrix, well, knowing that we have these unit vectors in there, we know exactly, so this is orthogonal unit vectors, okay? So E1 transpose E1 is the scalar product, this is the length of the vector, is 1. E1 is orthogonal to E2, that means like E1 transpose E2, this goes away, this is 0, and in the end we get the identity matrix. So to say, the transpose times the rotation matrix itself is equal to the identity matrix. Okay, that means, in other terms, you can, for example, multiply this. So we have this equation. You can multiply this from the left, from the right with the inverse of R. You have R inverse, which means here you get R transpose is equal to R inverse, what we have here. And essentially, this is the basic notion of orthogonality. So this is an orthogonal matrix, which means that the transpose is equal to the inverse. And this is quite handy. It's quite a helpful relation. Oh yeah, that's what it says. Yeah, and eventually what this leads you to is, having said the transpose is the inverse, it's pretty easy to see that because once you have the, which one? The rotation matrix that transforms from I to K. You take the transpose, you get actually the one that transforms from K to I. So pretty simple. So when you transform from one coordinate system to the other, you just take the transpose and you have the opposite transformation. And that's it. But that's not all of it. The important point is there can be, so this is the mathematical definition of a matrix being orthogonal, right? So that the transpose is equal to the inverse. But the determinant could still be plus or minus 1. What would it be if we have like a rotation matrix with the determinant minus 1? Okay, let's see what it means. Take the determinant and again use this this outcome that we had before, that the columns are just the unit vectors of the frame, of one frame representing the other frame. If you take a determinant, you know how to complete determinant? Essentially it's the wedge product, right? You take, it says here, this cross this times scalar product this. That's called the wedge product. Anyway, look at the math books, and this is the equation for the determinant. What you see is that what is it then? We have an orthogonal, we have a triad, right? So we have 3 orthogonal vectors that form a right-handed frame. And that's an important thing, a right-handed frame. 1, 2, 3. Okay, that's an important thing. So when I say like this, E2 cross product E3 gives you what? E1. E1, exactly. So this is E1 times E1, it's plus 1. Because it's a unit vector.
E1 not square.
Huh?
E1 mod square. E1 square.
Yeah. And this is 1. Oh yeah, I didn't say this, yeah. It's 1, exactly. Because E1 times E1 is 1. What if this what if this determinant would be minus 1? Huh?
Direction would change.
The direction would change, exactly. Then it would actually be the other way around. And this is what's used sometimes in computer graphics. Because now what we are after is like rotation matrices that should take a vector and just it's the same vector represented in a different frame. In image processing, sometimes you want to have distortion and so on, but also like reflections. Because this is what it does actually. Instead of just rotating it, you would reflect the vector. And that's exactly what we are not doing, but what sometimes is used in image processing. And they use minus 1. But still it would be orthogonal. Anyway, so our matrices, rotation matrices, are orthogonal and have the determinant plus 1, and so we have what we call rigid body transformations, because the length of the vector stays the same, and also the orientation of, I mean, a right-handed frame stays a right-handed frame. It doesn't become a left-handed frame, which would happen if you have the minus one determinant. Yeah, summary maybe. This is all too much, I know. We are not going to use this in detail, but it was important to say. And the only important thing is the notation. So let's say you have a vector with components expressed in frame J. You get the components of the same vector, because we are always talking about the same vector, right? Then expressed in a different frame, let's say I, by using a rotation matrix. Now the rotation matrix is called Rij. And that's a bit of logic behind it. So this is the source and this is the target, in the sense that the matrix takes as input the coordinates in a J frame, that's the source, and it transforms into the target frame, the I frame. So what comes out is the vector in the I frame. So whenever you do multiplication, I mean manipulation of equations and kinematics and so on, you don't necessarily have to understand what you're doing. Or you should, but anyway, there's a good way of checking at least if this makes sense what you have been doing, by looking into the indices, right? Whatever is on the left, on the most left-hand side, is supposed to be, of course, equal to this one. If this is not, and also you can only multiply elements that have the same index that matches. Yeah. Okay. And now comes this funny term here with the Lie group. Where's it going? I don't know. The Lie group is gone. Group. Ah, here. There's the Lie. Exactly. We don't lie. It's still Sophos Lie. I'm later on. I do a bit more on this, but anyway, these matrices we said actually they are orthogonal matrices with determinant +1. Okay. Now, when you multiply an orthogonal matrix, what do you get? Sorry. When you multiply two orthogonal matrices, what comes out? An orthogonal matrix. Exactly. If you multiply an orthogonal matrix with two orthogonal matrices with the determinant +1, what comes out? Exactly. It's an orthogonal matrix with the determinant +1. Number one. And also, for each of those matrices, there is a unique inverse, which is a transpose. And all this together makes them what mathematicians call a group, right? Because there's a multiplication, and you can, whatever you do with the multiplication, whatever comes out stays within the group. Whatever comes out is a matrix, is a rotation matrix in simple terms, right? It's an orthogonal matrix with the determinant +1. Plus there is an inverse. That's an important thing. So there is a unique identity element of this set, of this group. Anyway, this later on. And to give it a name, they call it SO3. So SO means special orthogonal, because we have orthogonal matrices, but special orthogonal matrices, because they have to have the determinant +1. And the 3 is just to say there are 3 times 3 matrices, or the other way of saying we are describing 3-dimensional rotations. You can do this in SON, right? But we don't necessarily look at, I don't know, space-time or so. Okay, so that's it. So and we keep saying that this matrix, I mean this rotation matrix, is an element of SO3. It's just a fancy name. It's nice to have it. Oh yeah, this is actually what I said already. So yeah, it's interesting. If you have time, you can make an exercise and show that the axis about your rotating is an eigenvector of the matrix. Anyway, you don't have to do this. But how do you see this? I mean, which vector actually, when you multiply the rotation matrix, there's one vector. Up to a scalar. There's one vector, a unique vector up to a scalar unique, that stays invariant. Which one is it? Huh? No. So you take a rotation, any rotation matrix, and you multiply it with the vector x, and what comes out is the vector x, maybe times, well, let's say just the vector x. Which vector is it? Don't think too complicated. We are talking about kinematics. So which vector stays invariant when you're rotating? Exactly, the rotation axis. Yeah. So the vector x is just a unit, any vector about the rotation axis. Good. Okay, this is another one topic. Oh yeah. So one more summary because it's so important. And that's why I put it together. I said it already. Okay. So this is important. So anyway, this is the notation we're using, rotation matrix, and then that is the transformation. Okay. Questions? No. Frame transformations, because this was only rotations. We have been saying that the rigid bodies the rigid body systems and the mechanisms that we're looking at consist of many bodies and linkages. And they are moving relative to each other, not only rotating, but somehow spatially moving. Okay? Okay, and that's why we need to look into translations plus rotations. Okay? And yeah, let's say we have again our body, our link, body, different, yeah, people call it link or body. And let's fix, before we go there, so let's fix one point. And I'm interested actually in the motion of this point. So let's fix, as I was saying, a rigid body is uniquely described or represented by a body fixed frame. So the whole thing is rigid, frame on it, so I know exactly at any time, relative to the red frame, where this point is located, right? Let's call this vector Q, and let's call this vector P, okay? Then, yeah, there's very complicated mathematics here. So the origin, no, what is it then? The vector P is just the origin, the vector to the origin called R, measured from the green frame to the origin of the red frame, and then from the red frame to Q there. So essentially P is R plus Q. I guess this is not too complicated. Again, this is not indicating any reference frame because I can only add vectors that are represented in the same frame, coordinate vectors. That's why we have to use the rotations and the indices correctly. So I don't know where to start. First of all, this one here. So this R1, 2. There's a bit of notation again. Maybe we should write something somewhere, or maybe you write it down. This notation means, look at this one first. This one comes then. So R1, 2. There are so many different notations out there, but in the end I ended up using this one for some time, and many people now do it. Essentially this says this is the vector that measures from 1 to 2. So this measures from two objects to another object. Between two objects. And our objects are frames. So frame 1, frame 2. So I measure, so I take the displacement from the origin of frame 1 to frame 2. 1, 2. So source target. Okay? Okay, but still, when I do computations, I have to represent it in some frame. And that's why we have the 1 on top of it. Now it becomes super complicated. It's not complicated, it's just unusual. Not used to it maybe. So anyway, so R1, 2 represented in the 1 frame. Because in the end, what I want is to have this P measured in this maybe space fixed frame or whatever it is. So F1 is the one with respect to I would like to measure the point, this point here. So, okay, so, and as I was saying, I take this one plus this one. So that one is?
The first one is the transformation, then rotation, or first rotation and then transformation? Sequence means, what is the sequence?
This one, this one?
No, from here, the green to the red, it is going, I think. Green to the red is the transformation, or rotation, means both are happening?
No, both at the same time. And exactly, this is actually what it's important. So, first of all, you have the, as I was saying, you can do, at the beginning, it's very simple, right? P is R plus Q. So, and as long as you're not using coordinate representations, frames, that's okay. But this is not helping us because we need numbers, we need to compute something. That's why we have to represent them somewhere. And now I would like to represent all the vectors in, or let's say the outcome of my vector P in the green frame. Okay, so I start with, for example, this one here. This is maybe the simplest one. So this one is represented in just the translation, only the translation. measures from here to here, from 1 to 2, is expressed in the one frame. And then I have the Q vector. I could have some indices here, but I don't need them later on, so I skip them. So then we have the Q, and for good reasons. We will always represent the vector in the body fixed frame. Why? Because it's constant, right? Because this point never moves on a rigid body relative to rigid body frame. And that's why I would like to represent this vector Q in the F2 frame. So, if it is in the F2 frame, then, well, I can't add them. I cannot say this one in the 1 frame plus this one in the 2 frame. This is not possible. I can only add vectors where we have at the most left side the same index here, okay? And that's why we have to multiply, we have to transform it into from the 2 to the 1 frame, okay? And what comes out, this whole vector is in the 1 frame, and of course this is Q plus R12, but now in the coordinate representation. Okay, and in the end, this is of course the transformation from point coordinates. You see, we have a bit more. We have the rotation that we had been looking before, but now we have the full kind of point transformation in the sense that I of course do the rotation of the, what is it then? The rotation of the frames plus the displacement of the, I don't know which one. Anyway, so the whole displacement. Okay. Yeah. So and this is probably what some people know already. This equation can easily be written in matrix form by using so-called homogeneous point coordinates. Okay. If you just do the multiplication, just multiply what happens here. So if you do this vector times this matrix, okay, what you get is like this matrix times Q2, I mean times the Q, which is this one, plus this vector times 1. So essentially this. So in the upper part, what you get, I don't have it here. Oh, anyway, yeah, in the upper part, I mean, what you get is exactly this. What you get is exactly this equation you get here. This is a bit of bookkeeping. You can say it's a bit of, you know, extra effort for no reason. This 0 and 1.
Dummy.
Huh?
Dummy kind of thing.
The dummy kind of thing, like it's just there to make it as matrix times vector, but it has some good properties. By the way, these when you have a vector, like a position vector, and then you add a 1 in the end, so you make out of a 3 vector a 4 vector. They call it homogeneous point coordinates. There is a good reason for calling it like this, but there's much more mathematics behind it. So essentially, this 1 has some sort of a homogenization property. Yeah. Anyway, so, and these matrices are known as homogeneous matrices. And I guess some people in robotics or in computer science, they maybe know this. No? Homogeneous transformation matrices? Okay, then you have learned something. So these are called homogeneous transformation matrices. And there are different symbols for them. I, in the past, for some years, I used C, capital C, because they do represent the configuration of a frame. But I don't know, I mean, many people use the H, and I swapped many reasons, because you have so many symbols, and in the end, the H is the best to use to avoid confusion. So anyway, so you have H and whatever. Some people use T for transformations and whatever. So H12 is the one, I mean, the homogeneous, the 4 times 4 transformation matrix. They're called homogeneous matrices. That transforms the point coordinate of a point expressed or measured from the 2 frame to the coordinate of the same point measured in the 1 frame. Right? So this is important because these are different vectors, not just rotated vectors, they are different vectors. They are always the position vector of a point measured from the 2 frame or measured from the 1 frame. So this is the meaning of that homogeneous transformation matrix. By the way, I put this in quotes because this term is, of course, absolute nonsense because nothing is homogeneous here. What they call it like this. When is a function homogeneous? What does homogeneous mean? Eh?
Equal to 0.
It should follow two properties. If it can be scalable.
Yeah, I mean, homogeneous is again a mathematical term, and so you have a function, for example. Can I write to this?
Yes.
Okay. So let's say you have a function of x, right? Okay. So, and if you, what happens if you say I have f of alpha x? So, and this is just a scalar. So, what can you say? Well, I don't know. It depends, of course, on the function, right? Now, what if the function is linear? If the function is linear, then f of alpha x is equal to alpha times f of x. What if it is quadratic? Yeah, but if it's quadratic, it's like this. No, not always. That's right. No, if it is homogeneously quadratic, yeah, that's the point. So anyway, so a matrix is homogeneous of degree k, so to say, if this is actually alpha to the power of k times f of x. Anyway, this is just, mathematics. I would just like to emphasize that this has nothing to do with this. I guess we are all... Yeah, any questions so far?
Any questions?
Otherwise we start from...
Till now.
Sir, we always transformation do from initial frame to body frame, like not body frame to initial frame.
Yeah, exactly, and this is the inverse.
Okay.
So when you do the inverse, wrong direction. When you do the inverse, so the question you've been asking, okay, now I have h12. The question is, what is h21? Well, pretty simple. You have a matrix. You just invert the matrix. And the good thing is, for this matrix, you can find a closed form inverse that looks like this.
Yes. Another part is we only do 3 degree of freedom like transformation, not rotational.
Oh no, this is including rotations. I mean, you have the rotation here and the translation.
No, rotational matrix, it include only translation part like 3 cross 3 matrix, na? Or also rotational part like.
I see what you mean. So okay. So these homogeneous. This is actually the next part of the. So we have points. We looked at points, right? Yeah. And the question is, what's the point measured from this frame and this frame? Eventually, we are only working with these matrices because the point. I don't really care about the points. What I care about is how this frame and this frame is actually relatively moving. And that's why you only need these matrices. So this matrix, this is the matrix I'm interested in. And then you have it all, because you have the relative translation of the 2 frames, and you have the rotation. So it's all this. It's a 6 degree, exactly, so it's a 6 degree of freedom relative motion.
Thank you.
Everybody hungry?